Amid the silent expanse of outer space, the comet designated 3I/Atlas will sweep by Mars. It appears to be merely one more icy wanderer at first glance. Yet researchers at Harvard are deeply concerned. Even with powerful streams of vapor erupting from it, the path of this object hardly wavers. This suggests that 3I/Atlas possesses an enormous bulk, tipping the scales at more than 33 billion tons, featuring a core as vast as a mountain range. Such dimensions dwarf those of prior extraterrestrial intruders by several orders of magnitude. If 3I/Atlas is indeed expanding in size, what makes it so resistant to the pressures that typically deflect typical comets from their routes? And should conventional theories fall short, what precisely might we be observing, whether on our planet or farther out? Determining the authentic orbit of something like 3I/Atlas demands a field that's equal parts artistry and rigor, astrometry. Observers worldwide train their instruments each evening on a dim point amid the moving lattice of distant stars. The objective sounds straightforward. Record the comet's precise location overhead to within a tiny fraction of an arcsecond. Achieving it, however, proves far more challenging. Contemporary imaging devices, called CCDs, detect the subtle radiance from Atlas's surrounding haze and identify its light's focal point, or centroid, with remarkable exactness. Top-tier facilities can produce location data from one-shot accurate to mere milliarcseconds, finer than a strand of hair viewed from a mile off. Yet no reading exists in isolation. Every photo gets compared to a directory of benchmark stars, positions refined by efforts such as the Gaia mission to levels of fidelity unimaginable just 10 years back. The procedure demands utmost care. Instruments' timers align with universal coordinated time, and each capture bears an exact timestamp. Minor mistakes, such as relying on regional hours over UTC or consulting obsolete stellar lists, can shift the perceived spot by a detectable degree. To counter this, groups employ probabilistic adjustments, realigning each evening's figures with the most current celestial maps and marking sites that repeatedly deliver anomalous readings. What emerges is a chronologically marked log of Atlas's path. Every entry stems from thorough positioning, tuning, and mistake verification. When experts discuss deviations in the trajectory, those slight variances between Atlas's predicted spot and its real one, they depend on this groundwork. Trust in subsequent assertions regarding its weight, speed up, or uniqueness builds upon these regular observations. Absent such exactitude, the narrative of 3I/Atlas would dissolve into the cosmic clutter. Prior to validating any assertions on Atlas's dimensions or heft, the Harvard data processing team tackled a challenge as formidable as the sightings, stripping away concealed distortions from the records. Once purified, the figures revealed an unanticipated tale. Through aligning photometric observations from scores of scopes, specialists established Atlas's visible luminosity over various evenings and wavelengths. This relied on a few key premises: the core's reflectance, or albedo, ranging from 0.04 to 0.06, consistent with the murkiest comets on record, plus a reasonable spectrum of densities spanning fluffy frost to compact stony compositions. Input those into the conventional formulas, and calculations indicate a core spanning roughly 5 kilometers. That's not merely large for an interstellar arrival, it's substantial outright. The majority of comets venturing into the Sun's inner domain measure far smaller. Even giants like Bernard and Ellie Bernstein, dubbed the Colossal Comet, barely surpass it. But the real surprise comes next. Assessments of forces, drawn from path deviations and the visible gas envelope, reinforce this projection without alteration. The detected non-gravitational push, under 15 m per day squared, is minimal enough that, given the evident vapor release, only a hugely heavy form could avoid veering astray. The evidence aligns. A core spanning at least a few kilometers, with overall weight surpassing 30 billion tons. This outcome endured scrutiny across all variations the specialists tested, simulations via Monte Carlo methods, density modifications, even differing dynamics frameworks. In every case, the minimum estimate remained firmly elevated. For the initial occasion, the roster of interstellar comets gained a true behemoth, sending waves of intrigue across the entire scholarly field. Astonishment struck the Harvard collaboration just before sunrise. The conclusive weight estimates had scarcely spread when communication threads lit up with skepticism. Among interstellar entities, scale defines significance. And Atlas's metrics didn't merely exceed norms, they demolished them. To illustrate, all previously documented interstellar bodies, from Oumuamua to 2I/Borisov, resembled mere space debris in contrast, compact enough for a mere burst of gas to alter their course. At beyond 30 billion tons, Atlas loomed unparalleled. Standard theories, grounded in decades of detection trends, forecasted that an active interstellar giant of this scale ought to be extraordinarily uncommon. So uncommon, indeed, that some experts once contended that spotting a kilometer-sized, outgassing interstellar body within a single human lifespan was unlikely. But within mere hours, the upheaval extended far past Harvard's confines. Urgent virtual meetings pulled together specialists from NASA, the European Space Agency, and the Minor Planet Center. Calculations were verified repeatedly, scrutinized multiple times over. Still, the estimated mass remained steadfast, regardless of the analytical pathways used. Certain investigators delved into existing studies in search of reasonable anomalies. Meanwhile, others immersed themselves in demographic simulations, attempting to reconcile this discovery with projected occurrence rates. The conclusion invariably echoed the rest. The probability of detecting a structure of this scale in today's observing period was, at most, exponentially slimmer than encountering a diminutive interloper like Oumuamua. Prevailing frameworks indicated such a sharp decline in likelihood that Atlas's emergence seemed akin to a rare anomaly in the data. Apprehension permeated every discussion. A few advocated restraint, invoking potential overlooked distortions or unaccounted physical principles. More forthright voices deemed it the least likely breakthrough in years. By week's close, agreement shifted from defining Atlas's essence to affirming its extraordinariness. The discipline faced an enigma that challenged the figures, with the quest for resolution just underway. Discussions on 3I/Atlas's authentic character span a wide range, from solidly confirmed elements through credible yet unverified traits to purely conjectural notions. At its core lies the prevailing perspective. NASA, ESA, and the majority of planetary experts characterize Atlas as a substantial organic interstellar comet. Its surrounding haze, core dimensions, and path align with the expansive, albeit extended, parameters of cometary behavior. Official releases emphasize prudence, highlighting solid weight assessments while calling for patience amid additional spectral analysis and visual observations prior to overhauling established knowledge. The phrasing stays deliberate, almost certainly a comet, as a JPL expert phrased it, though the size projection. I'll rest easier after reviewing the Mars flyby readings. Building on this foundation, a set of credible yet atypical attributes stirs greater intrigue. For instance, Atlas's trajectory lies almost flush with the ecliptic plane, the orbital layer of the primary planets. This represents an uncommon alignment for an extragalactic arrival, whose courses typically veer at sharp inclines. Its route grazes Mars before heading to Jupiter, resembling a precise celestial maneuver. A few scholars propose this might stem from chance selection or signal uncommon evolutionary paths in distant stellar environments. Nevertheless, such concepts stay grounded in feasible, if unlikely, natural processes. On the conjectural fringe, Avi Loeb and select associates have proposed that Atlas could transcend mere cometary status. Their case rests on the discrepancy between mass and motion, plus the orbital symmetry. Loeb presents these as unresolved inquiries rather than firm judgments. Should 3I/Atlas prove a billion-ton entity bucking our theories, we ought to entertain unconventional options while adhering to empirical findings. The notion of a technological relic, like a constructed scout or abandoned craft, resides in this territory, fascinating yet lacking tangible support. NASA and ESA counter firmly, cautioning against unchecked conjecture outpacing verifiable sightings. Visual aids depicting assurance levels now feature in numerous talks, confirmed, feasible, hypothetical. Every assertion positioned by its supporting proof. As monitoring efforts intensify, the community clings to a fundamental guideline. Bold assertions demand robust validation. David Fner's concept of planetary inception via interstellar captures extends the conversation beyond our system into broader cosmic development. In his computational runs, nascent stellar setups don't merely gather nearby debris. They function as interstellar traps, ensnaring rogue wanderers that venture near. The reasoning is straightforward. Heavier stars form grander, thicker accretion disks, extending their gravitational influence. In principle, this boosts their odds of grabbing transients, such as 3I/Atlas. Yet, upon close examination of the modeling, enthusiasm wanes. Retention probabilities rise with star size, but the figures stay modest. Under ideal conditions, just a few interstellar items are anticipated to get held during a disk's brief active phase. Referees dissecting the results from Fner's work doubt if the documented count of comparably sized entities suffices to yield meaningful impact. A remark from a 2025 review process surfaced. The idea is sophisticated, yet the data doesn't favor it. The wider cosmic implications stand out. Should interstellar captures drive planet building, each find, particularly a hefty one like Atlas, might bridge gaps in the emergence of gas giants near massive stars. Still, proof stays indirect. No concrete instance exists of a snared body igniting planetary growth, and event rates lurk under veils of doubt. Fner's charts reveal a general pattern. Larger stars could theoretically haul in more interlop, although cosmic debris might suggest origins from disrupted planets. Current simulations fall short of precisely measuring the extent of this influence or determining if it's significant enough to impact entire galaxies. For the time being, the notion of seeding worlds remains in a speculative realm, creative and supported by equations, yet without the solid data needed to elevate it from hypothesis to principle. As monitoring efforts intensify, researchers are on the lookout for indicators that could sway the discussion, such as unique isotopes, peculiar dust compositions, or orbital hints pointing to an authentic extraterrestrial source. In the meantime, the conversation persists, grounded in potential but tempered by doubt. The anticipation builds truly now that C/Atlas hurdles toward its upcoming encounters. Coordinators from agencies spanning 3 continents have pinpointed 4 key moments, each offering chances for discovery alongside uncertainties. The initial one arrives in early October. Mars Express and ExoMars TGO, both circling the red world, plan to direct their imaging and analysis tools at the interstellar comet during its flyby, coming within millions of miles. Schedules are precise, with last-minute adjustments frequently sent just hours prior to the nearest pass. Instruments built to study Mars's atmosphere will instead probe for subtle signs of water, carbon dioxide, and metallic elements in Atlas's surrounding haze, aiming to detect the earliest chemical markers from beyond our solar system. Toward the end of October comes perihelion, when Atlas reaches its nearest point to the Sun. Here, Earthbound observatories can't track it amid the intense solar brightness. Solely probes positioned appropriately, whether in solar paths or following Earth, will observe its behavior. Specialists at the Minor Planet Center and ESA's Solar Orbiter collaborate on notifications, monitoring for abrupt variations in luminosity or path that could indicate fresh outbursts or alterations in form. Come December, Atlas reappears from the Sun's glare and heads into its post-perihelion trajectory toward Earth, at about 170 million miles away. This phase opens opportunities for the James Webb Space Telescope and Vera C. Rubin Observatory. They'll pursue detailed spectral readings to identify isotopic signatures and grain makeup that might illuminate the visitor's beginnings. Lastly, in March 2026, projections show Atlas grazing just above Jupiter's upper layers, potentially as close as 33 million miles. NASA's Juno, in its polar path around the gas giant, could be redirected to collect particles from dust trails, pending approval from operations leads. Every phase challenges equipment, strategies, and the hypotheses surrounding this remarkable wanderer. All scientific groups maintain an active roster, a dynamic inventory of observations that might resolve the question of whether it's purely natural or something more unusual. Leading the priorities: isotopic proportions in the emitted vapors. Should Atlas's hydrogen or carbon variants deviate sharply from typical solar values, it might indicate formation outside known galactic structures or unfamiliar formation mechanisms. Following that, the ratio of dust ejection to motion changes. The reasoning is straightforward. If substantial dust release persists without noticeable path deviations, the estimated weight becomes even more substantial. A discrepancy, abundant particles yet minimal influence, would raise alarms about concealed bulk or atypical influences. Examining rotational forces appears on every planning board. Active comets typically betray their activity through rotation. Expelling gases function like small engines, gradually altering the core's turn and causing detectable fluctuations in brightness patterns. Should Atlas exhibit unchanging spin or force effects unmatched by visible emissions, experts will seek other interpretations. Frequent imaging from the Rubin Observatory and JWST will detect these tiny variations, occasionally mere fractions of a degree daily. Compositional analysis completes the agenda. Atypical heavy elements, particularly nickel-to-iron balances, face close inspection for evidence of separation or deliberate enhancement. Unprocessed data from Keck and JWST records will undergo meticulous review, scanning each feature to eliminate instrument flaws before advancing bold assertions. Each fresh observation, an odd isotope, a shortfall in dust effects, an unexpected spin quirk, arrives like a vital hint. As the journey progresses, the case accumulates, and the community anticipates the breakthrough that will settle the matter. Harvard's examination verified that C/2025 A11/Atlas possesses a core almost 5 kilometers across and a mass surpassing 33 billion tons, rendering it at minimum 1,000 times more massive than prior interstellar objects. Even with evident gas releases, its extragravitational pull stays under 15 meters per day squared, a discrepancy that challenges conventional comet behaviors. Although most organizations uphold a conventional formation, the scale and near-plane trajectory have ignited discussions, encompassing ideas of engineered relics and world-building functions. Planned close passes, Mars Express and ExoMars TGO in October 2025, JWST and Rubin post-solar alignment, plus a potential Juno interaction at Jupiter, promise the crucial insights. Isotopic balances, particle emissions, and rotational adjustments. So far, less than 1 enemy none of the discovered interstellar visitors align with even 1/3 the mass of ice-covered Atlas. The next few months will challenge every hypothesis available. Right now, the findings highlight a single undeniable point. 3I/Atlas differs from all prior discoveries. Its genuine character stays unresolved.